Just going to look at some properties of complex conjugates that allow us to manipulate in some questions. Okay, the first couple we saw when we looked at the Argand diagram. The modulus of z will be the same as its conjugate. Remember we said conjugates were reflections in the real axis? So their actual distance to the origin is the same. Or another way of thinking about it, if you square the real part and square the imaginary part, you're going to get the same amount, because the only difference is the imaginary part is the negative. Well, when you square it, the negative doesn't matter. So the modulus of a number and the modulus of its conjugate will be the same. The arguments, however, will be opposite in sign. And again, that comes from that reflection in the real axis. One would have a positive theta and one would have a negative theta. Mentioned this a few times, but I'll mention it again, seeing we're talking about properties of conjugates. Number times its conjugate will be the sum of the two squares. So the real part squared plus the imaginary part squared. Another way of saying is, well, it's the modulus squared. And we did mention this before, but we can do it in any order. You could add the numbers first, then find the conjugate, or find the conjugates and add them together. It will come up with the same result. Same with multiplication. Same with division. And then the other one you may remember we talked about was the quick way of finding the reciprocal of a complex number. You find its conjugate, you put that on the top, and on the bottom goes the modulus squared. Here's a really interesting question, which if you do it one way, can take a long time. And I think I might have even set a similar question to this in the exercise, one of the exercises, except instead of numbers that had a plus ib and all this, you had to prove a squared plus b squared or something like that. And it was a bit mean of me setting it to you back then, because doing it this way is so much quicker. Watch how I'm going to do this. If x plus iy is the square root of 6 plus 2y and 3 minus I, we're going to show that x squared plus y squared is equal to 2. So what you probably would have done in the previously is you would have worked out what 6 plus 2i on 3 minus I is, found its square root. That would have allowed you to find the real part and the imaginary part. Then you could square them and you get that it's 2. I'm going to do it this way, playing with the conjugates. X plus iy is the square root of 6 plus 2i and 3 minus I. So if I square both sides, I'll get x plus iy squared is 6 plus 2i on 3 minus I. But if I take the conjugate of both sides, remember, I just said I can do it in any order. So what I've written down is the conjugate of the final result. But I could have done that as, I'll find the conjugate of the top, divide by the conjugate of the bottom. And when I find the conjugate of x plus iy squared, I could have found the conjugate first and then squared that. Or I could have squared it, then found the conjugate. So the conjugate of x plus iy squared would be the same as x minus iy squared. And the conjugate of 6 plus 2i on 3 minus I will be 6 minus 2i on 3 plus I. I'm now just going to multiply these two expressions together. X plus iy squared times x minus iy squared, well, they're conjugates. Multiply conjugates together, you get the sum of two squares. So on the left-hand side, I get x squared plus y squared squared. On the right-hand side, each of these are conjugates as well. So I also get the sum of two squares. So on the top of the fractions, I get 36 plus 4, the bottom 9 plus 1. So x squared plus y squared squared is 4. So therefore, x squared plus y squared is 2. Can't be negative 2, because remember, x and y are real numbers, and so when I square them, I must get a positive number. So that's a very quick way of coming up with that result, just by playing around with conjugates. All right, I'm going to give you 6 questions to do today out of Patel. That one's out of. So 4H in Patel, and it's just playing around with conjugate ideas.